Okay, let's go for chapter 25. It's gonna be current and resistance. The symbol for current is I, for resistance is R. Let's define current in this way. Let's take a wire, right? So wire, and let's take current in that direction. Now let's take one point as a reference, and let's count how much charge is crossing that point per time, per second. So we define then the current, so definition, right? Let's use the average, the change in charge, right, with respect to time. Now what happens if the current is not constant? Well, in that case we can use the infinitesimal changes of that current with respect to time. So we can take this as the definition for current, right? Change in charge with respect to time. Now this is a new quantity, so we need the unit. The unit for charge is gonna be always called amp or ampere. The symbol is A. In this case, right, 1 amp is equals to 1 coulomb per second. Okay, and this is the definition for current. When we're dealing with current, we take the positive charges to be the particles that move, the charged particles that are in the current or produce the current. And this is called the conventional current. That's the convention. And also we have negative charges moving, correct, in opposite direction. Those are the electrons. But by convention, we take the positive charges to be the charge that move. Okay, great. Now, when we're dealing with current, we have two types so far, right? Current. We divide this into two groups. We have direct current, right? DC. The main source is the battery. It's produced by the battery. And we have the alternating current. Right, and this is AC, and the source is the generator. Okay, so at this time, at the beginning, we start with the direct current using batteries. Okay, perfect. Now, when we have a wire, right? Imagine this is the wire right here. Take into account, right, this section, this small section the X, and this is the area, right? Imagine that's cross-section area. Also, we have the current in that direction. Remember, we have the conventional current, which is using positive charge in motion. Now, let's try to find, in this case, current. What should be the current taking into account the charges? Okay, let's do it. So current is equals to this change in charge with respect to time. Correct? But let's involve right here at the area, right, and the distance and so on. Let's see what happens in this case. Let's involve the concept of density. Density is defined as the charge divided by the volume. Because this is constant, also we can use right this quantity, the change in charge respect to change in volume, infinitesimal volume. Correct. Now we can, because over here we have this charge, so we can solve from here, right? This dq equals to density dv. Okay, let's do it. So now be density change in volume, correct, respect to time. But what is the volume? The volume that we are dealing with. This is the volume right here, right? This is the volume. This is the area, and this is the thickness of this segment, this volume. But in this case, one more time, this change in volume is equals to, for this cylinder, is gonna be area dx. Correct? When we substitute this value right here, what do we have? Well, this is equals to density dV is gonna be area dx divided dt by dt. Now this quantity is velocity, right? This is called the drift velocity, correct? So this is this quantity is called, right, the drift velocity. Drift velocity, correct? And then what do we have? Well, current takes this form, density, area, this drift velocity, that's the velocity, correct? I forgot something, and that's now divided by, something is missing right here. Okay, let's see, this is the velocity acceleration, this area, well, we have that quantity in this part. Perfect. Now, let's go back to density. What do we have in density? Well, one more time, let's go to this equation right here, correct? So density is equals to charge, right, divided by the volume. But this charge is the total charge. So this equals to the numbers of these particular charges, right? Let's say this is Q. The whole thing is gonna be BQ, correct? Divided by the volume. Now, this quantity is numbers of particles per volume. Let's define this as n, right? Little n. And when we do that, what do we have? Well, in this case, we have that the density is equals to n times the charge, individual particles. Now, when we substitute this value right here, what do we have? Well, from here we have that the current is equals to n, right, times the charge times area times this drift velocity, right? So we have again this equation that help us to, right, calculate the current using the particles, charged particles, right? And also using the dimension of the conductor, in this case the wire, correct? And the drift speed. Now, if we divide this by the area, it takes a special name. Current divided by area is defined as the current density, J, right? Current density, correct? Also, in this case, current density is equals to, one more time, is the current divided by the area, but current divided by the area is also equals to n, right? Numbers of particles per volume times the charge times the drift velocity, right? We can take also this as a vector in this way, correct? And this is the, now we can do it this way better. Okay, this is the magnitude. Also, we can say that the current density is equals to, right, numbers of particles per volume times the charge times the drift velocity as a vector now. Okay, perfect. Now, let's go to the next topic. The next topic is gonna be resistance. The symbol of resistance is R. Let's try to create a formula. Imagine that we use water. Okay, let's compare this current with water. Okay, and what do we have at the beginning? If we have a pipe, this is water, for example, water. If we have a pipe, right? This water produces a resistance, right? For this length. What happens if we increase the length? Resistance 1. Well, if the length, right, of the pipe with water increases, right, the resistance changes, increases too. So it means what? That the resistance is proportional to the length. Also, if we take into account the diameter, so one diameter, right? If we increase the area, the cross-sectional area, right, it's found that the resistance decreases. So the resistance is inversely proportional to the area. Correct? The same thing happens to current. You will have a current through a wire, and we increase the length of the wire, the resistance increases. The resistance to the current, right? What happens if we increase the thickness, right, or cross-sectional area of the wire? Well, the resistance decreases. Correct? Now let's combine these two. What do we have? Resistance is proportional to L over area. Okay, how do we eliminate this symbol? Using a constant. So the resistance is equals to a constant rho called the resistivity times the length divided by the area. Okay, rho depends on the material, could be copper, aluminum, right, and so on. This is called the resistivity. Resistivity. So we have one of the equations for our resistance, resistivity L over area. Okay, but this resistivity depends on temperature. So it's found that resistivity is equals to the initial resistivity, right, times 1 minus a temperature coefficient of resistivity times the change in temperature. Correct? So this is for resistivity, correct, dependence with the, that depends, right, on the temperature. The same thing happens to the resistance because they are proportional, right? They are proportional. The same thing happens to the resistance. At the beginning we have the final resistance, right, is equals to the initial, right, times this quantity. That again gives us the relationship that the resistance depends on temperature too. This is from the experiment. Okay, if we increase the temperature of, let's say, the conductor, the wire, right, the resistance increases too. The resistance increases, the current decreases. Okay, perfect. Now let's see what happens when we are dealing with potential energy. Let's go to potential energy. When we're dealing to potential energy and relate this to current, this is similar to have, for example, water. You have water right here, right, container, correct? And we connect these two containers, right, which are at different pressure, right? Because there are different pressure, we have right here a current through this pipe. Let's say we have current through that pipe. The speed of how much current goes through this pipe depends on the difference in pressure, right? After a while, right, if we keep open this pipe, after a while they reach an equilibrium and no more current. So we have current, in this case of water, if, right, there is a difference in pressure. If there's no difference in pressure, the current is zero. The same thing happens to charges, right? We have a potential difference, right, on this part, and potential difference on the other object, right? If we connect these two, we create current, electric current. But later, right, these two are in equilibrium and there is no more current between these two objects. Now, if we increase the difference, means we increase, in this case, the pressure, or we increase the potential, correct? We increase the current. Remember when we're dealing with charges, we present this in this way, right? This is high potential, this is low potential, correct? And we call this our voltage, for example, correct? If we increase this difference, well, we increase the current. Imagine current is going in this way, current. And also we have, right, friction. Friction, remember, is related friction to resistance. We have some resistance or some friction, right, to the motion of the charges, correct? So we have this current. Now let's see what happens. Well, again, this is potential difference. Let's pay attention on the current. Okay, so the current if we increase the voltage, right, if we increase the height, let's say the separation between these two charges, correct, we increase the current, right? So the current is proportional to the voltage, right? You increase the voltage, we increase the amount of current. Now, what happens? This is the case when resistance is constant, okay? When R is constant, we have this condition. What happens if the voltage is constant? When V is constant, and now we change the current. If V is constant and the resistance increases, if the resistance increases, the current decreases, right? So we can represent this in this way. The current is inversely proportional to the resistance. If the resistance increases, the current decreases when V is constant. Right here, the opposite. When the resistance is constant, the current increases when the voltage increases. Now let's combine these two, and what do we have? We have that the current is proportional to voltage over the resistance. Now we need to eliminate this symbol, right? And then what do we have? Current is equals to, let's say, a constant, right, times voltage over resistance. Remember, this is the constant of proportionality. And the main function is to match the unit. Now let's see. So far we have the units for current, which is amps, the units for voltage, which potential difference, which is volt. All right, now let's define the units for resistance to find what should be the units for the constant of proportionality. Let's do it. Look, let's define the units for resistance to be equals to volts divided by amps, right? Volts divided by amps are the units for resistance, right? And this, it has a special name called ohms, right? Gonna be 1 ohm, right? The letter is omega, what we call it ohms. How many ohms? Okay, perfect. Now, when we substitute this value right here, we find that K is equals to 1. But from here, K is equals to 1. When we define the units for resistance to be volts over amps, we find that K takes the value of 1. So what do we have then? Well, we have this equation right here, that current is equals to voltage over resistance, or we can say that voltage is equals to current times resistance. This one has a special name. This is called the Ohm's law. Ohm's law. And this is valid only when R is constant. Remember, we mentioned that R, the resistance, depends on temperature. Now, when R is constant, now we can apply this condition, this relationship, right? Voltage equals to current times resistance, Ohm's law. Perfect. So voltage is equals to current times resistance. Remember, the unit for resistance is called ohms. Okay, perfect. Now, let's go to a circuit. Let's go to circuit. These are the main part of a circuit. Circuit. These are actually the circuit element. Circuit element. We have the resistor, right? This is the symbol is R, and the main function is to dissipate energy. The resistor, right, dissipate energy. Dissipate, right, energy. that happens using heat, right? By heat, right? Perfect. Using heat in this case. Heat. Great. Heat. The next element for a circuit is gonna be the capacitor. We already covered that one, right? Capacitor. This is a symbol. Remember, this is C. And the main function for a capacitor is to store charge and energy, right? Stores, right, charge and energy, electric energy. Great. The next element is gonna be the inductor. That's the symbol for inductor. And the inductor stores magnetic energy. And the last one is gonna be the voltage source. Voltage source. And we have two. We have the battery and we have the generator, right? The battery, that's the symbol for the battery, positive, negative, and we have the generator. That's the symbol, right? As a wave. So these are the elements for a circuit. Correct? Okay, now we have the simple circuit, correct? We have the battery, we have the resistor, correct? And we have the current. This is the resistance, this is the battery, and we have the current. The main three elements so far, this is one, the simplest one. We already covered one before, right, in the previous chapter, which is we have the voltage, we have the capacitor. We already covered one, right, capacitor, voltage. But in this case, we have no current yet. But in this case, correct, we have a current, we have voltage, and we have the resistance. And we can apply now Ohm's law, right? Ohm's law. Remember, the current is the conventional current. Also, we have right when the electron moving, that's the electron flow. We're dealing with electrons. But by convention, we in general use the current from positive to negative, the conventional current. Okay, perfect. Now, let's do one example. Let's try to find the drift velocity. Imagine that we have a wire with electron with some current, correct? Let's do this example, please. This example we have copper, we have copper wire, correct, with a current equals to 5 amps, correct, and we have a cross-sectional area equals to 0.05 square centimeters. And using this, let's find the drift velocity. Okay, let's do it. What should be the drift velocity? Well, from these equations, we can find it using this equation because we already have the area and we have the current. Let's solve for the drift velocity. It's equals to what? It's equals to current divided by n times the charge times the area, correct? Perfect. In this case, this is given, it's provided, this is given, also the charge is given. We need to find the numbers of particles per volume. Let's do it. How we define this N? N, what N is equals to numbers of particles per volume. But what is the numbers of particles? Well, in this case, we use numbers of moles. Remember, numbers of moles. This is mole. This is different. This is numbers of moles. This is equals to numbers of particles divided by Avogadro's number. Is also equals to mass of the substance divided by the molar mass. Correct. Now from here we can solve for n. N is equals to mass times Avogadro's number, right, divided by the molar mass. Okay, when we substitute this value right here, what do we have? This equals to mass, correct? What else? Avogadro's number divided by V right here, divided by molar mass. Now, what is this? Well, that is equals to, this is equals to density, but this is density of copper, right? Copper times what? Times Avogadro's number divided by molar mass. Great, but the density for copper is given, density for copper, right, is equals to, this is from tables, 8.9 times 10 to the third kilograms per cubic meter. Also, the molar mass for copper is given, it's gonna be 63.5 times 10 to the third rate kilograms per mole. Correct? So everything is given, and then we can solve for this drift velocity. Okay, let's continue right here. Is equals to current. Okay, current divided by N is equals to what? Density of copper, right? Avogadro's number times the molar mass. Also divided by the area over here, right? The area. Also the charge, right? Oh my God, I forget it. No, okay, this is actually the charge, right? No, that's the density, right? That's the density. Right here, I forgot the charge. Okay, let's write the charge right there. Correct? And, well, let's substitute the values and see what do we have. What is the answer for this particular example? The drift velocity is equals to, what is the current? The current is given is 5 amps, right? What is the molar mass? Well, it's given 63.5 times 10 to the minus 3, right, kilograms per mole. Divided by density. What is density? 8.9 times 10 to the third, correct, kilograms per cubic meter. Yes. And then times Avogadro's number, which is 6.02 times 10 to the 23, right? Molecules per mole, correct? Times the area. There's gonna be, where's the area over here? Gonna be 5 times 10 to the negative 6, correct? Square meters. And finally, times the charge. The charge is equals to, 1.6 times 10 to the negative 19 coulombs. Okay, when we do these calculations, the drift velocity, right, is found to be equals to 7.4 times 10 to the minus 5, right, meters per second. So you can see, actually the electrons, when they're moving without velocity, they're moving in a straight line, right? They're moving right randomly, but the net velocity, let's say in the direction of the y, direction of the field, right, is gonna be this velocity, right? But in general, the electron moving right randomly, right, up and down, let's say in zigzag, but the net velocity happens in one direction, and that velocity is called the drift velocity. Okay, perfect. Now let's go for the next topic. The next topic is gonna be the electromotive force. Okay, let's go to the electromotive force. Electromotive, right, force. Also called, the symbol is, that symbol also is called EMF. EMF, correct? Electromotive force. At the beginning, it was believed it was a force. Today, we know that this is actually a voltage, right? This is the voltage or potential difference when we're dealing, for example, with a battery, for an ideal battery, right? When there is no resistance inside of the battery, correct? Or when the battery is not connected yet to a circuit. For example, if we have this is the circuit, correct, and is an open circuit, if we measure the voltage of the battery, we take this as the electromotive force. Now, when we close the circuit, remember this is the resistor right here. When we close the circuit, correct, we close the circuit. Now we call this voltage, let's say FB. In general, right, when the battery is ideal battery, we can take that the voltage is actually the electromotive force. Right? In general, one more time, when the battery is connected to a circuit and we measure the voltage using a voltmeter, that's gonna be the electromotive force. When we connect the battery to the circuit, that's gonna be the potential different, the voltage of the battery. It's gonna be a little bit different. Depends on the battery. If the battery is new, right, this is about the same. If the battery is old, the battery creates a resistance. Why? Well, because now the battery is part of the circuit. Correct? Imagine that this is the battery right here. Right? That's the battery. So the battery inside has a resistance. Correct? Imagine this is the case, and this is the circuit, right, of which it is connected to. Right here we have an electromotive force, and inside we have this internal resistance. Correct? This little r is called the internal resistance. Internal resistance. When this is very small or zero, it's a brand new battery, of course these two are the same. The voltage of the battery and the electromotive force, they're the same. But again, if this is not a brand new battery or ideal battery, I will have to take into account this resistance, because now we have a current, right? A current that makes a circle. Remember, when we're dealing with a circuit also means a circle. What to make circles, right? Circles. When we make a circle, this resistance, internal resistance, is part of the circuit, right? Or the circle. We need to take it into account. So in general, we have that the voltage, right, or potential difference is equals to the electromotive force minus, right, because right here we have a current in this direction, we have a current in that direction. This product, right, current times resistance is equals to voltage, correct? And also right here, current times this internal resistance also equals to voltage, correct? So this is equals, this is voltage, the units are gonna be volts, also the units are gonna be volts right here. It's gonna be in this way, correct? It's gonna be the voltage of the battery is equals to electromotive force minus, right, the current times the internal resistance of the battery. Okay, perfect. Great. Now when we're dealing with batteries, we can arrange the batteries in these two ways too. We can arrange the batteries in series and in parallel, in the same way we did with the capacitors in the previous chapters, remember? Okay, imagine that we have a set of batteries right here. Okay, 3 batteries. Remember, they have positive and negative, right, terminal, positive, negative, correct, positive, negative. Now let's connect this in this way. We'll connect these batteries in this way. These are in series, right? Cells in series. The notation, interpretation like this, right? These are in series. That's the voltage. Okay, when that happens, let's see what happens to the current. In this case, the current is the same through all of these wire, right? Current, let's say what? Current 1, current 2. Actually, let's call this the total current. Okay, current through 1, current through 2, and current through 3. Imagine. Okay, so the current is gonna be the same when we connect these batteries in series, but the voltage is not the same. The voltage is equals to the sum, right, of all the voltages. This is again V1, this is V2, this is V3, correct? V2 plus V3. Okay, what about in parallel? Cells in parallel. Okay, let's do it. When we have cells in parallel, imagine that this is the top view of these three batteries, and this is positive. Mine is positive, this is negative. This is positive terminal, negative terminal, correct? Right, positive and negative. Now we connect these together. These are together, right? And the negative together too. Correct? And these are in parallel. Well, we have something like this, right? The same thing as before, correct? These are in parallel, like this. Okay, perfect. Now let's go to current and to voltage. In this case, the current is this, the torque current is the sum, right, of all of this current. This is current 1, right? Current 2 and current 3. Okay, so what do we have then? Is the sum current 1 plus current 2 plus current 3. That should be the torque current. What about for voltage? In this case, voltage is the same for all of these batteries in parallel. Correct? This is the case when we're dealing with cells. Sometimes in the circuits we have something like this, right? We have a resistor, and then we have a battery, and then we have another resistor, and then we have another battery, like in this case, right? Imagine this is positive, negative, positive, negative. What happens? Well, on occasion this way, negative, positive to match this one, right? Negative, positive, right? When we go from negative to positive, negative to or positive to negative, right? We are adding, right, the voltages. When we go to the other side, right, like in this way. Now in this case we subtract, right, these two voltages. Okay, perfect, great. Now let's go finally to the last concept in this chapter, which is power. Let's do it. Power. Power has the same meaning as mechanics, right? Power, remember, is defined as work divided by time, or we can define it as because work, remember, we can use work. Okay, let's do it. Power equals to work divided by time. Also, if we're dealing with potential energy, we found that work is equal to negative, right? The change in potential energy, correct, of this the system, right? So in this case, we can say that this equals to change in potential energy, correct, divided by the time. The same ideas. So we use this concept right here. We have the derivative of the small changes of this electric potential energy respect to time. We define in this way the electric power, right? Electric power. Let's do it. So electric power, then power is equals to this change in the electric potential energy divided by the time. Also, when we use work, right, we can find that power is equals to this change, that's also equals to the voltage, which is A and B, times change in charge, right, with respect to the time. Correct? Okay, because remember what happens? Well, how do we define this? Remember this voltage, right? Is equals to what this change in potential energy, correct? Divided by this test charge, correct? And when we solve for this quantity, well, we create this condition right here. But what is this? That's the definition for current, right? So it's equals to current times this potential difference or voltage at A due to B. Okay, perfect. Or with respect to B. Okay, great. So we have another equation for power. Power is equals to current, right, times, usually we use average right here, average power times this voltage, correct? Also, we can use Ohm's law right here, plug it right here. What do we have? So it's equals to gonna be current squared times the resistance. This is a very important quantity, okay? This product, current squared times resistance, right, is the power lost by heat. When we have friction, by heat, correct? Right, when we have a large current through a wire, because a resistance becomes hot, right? So some power is being lost, and that's the product that gives us how much power is lost, and that energy is converted to heat. Okay, perfect. Now, also from Ohm's law, we can solve for current. Current is equals to voltage over R, the resistance. Now we practice in the original equation right here, and what do we have? It's gonna be voltage squared divided by the resistance. So three different ways how we can represent power, electric power, for being calculated. Correct? Great. And now we can apply also to the battery, because this chapter is dealing with batteries, electromotive force, and so on. So we can find that the power is equals to, right, this current times this voltage. We define right that from here, look, is equals to current times what? Electromotive force times or minus current times the internal resistance. So this is equals to electromotive force times the current minus current squared times the internal resistance. Right? Perfect. So it's another way to represent power, but in this case using the battery, the electromotive force. Correct? Great. And with this, we finish this chapter 25, and see you in chapter 26. Okay, thank you. Bye.